Thank you so much for having me here. Like introduced, I will present our work on the potential of large language models for construction quotation workflows. This research was carried out together with Žiga, Krvina and Klinc at the University of Ljubljana. And we focus on a practical use case from geotechnical engineering, so preparing quotations from client inquiries. So quotation preparation usually begins with a client email, often accompanied by PDFs, drawings, and other project documents. So an engineer has to interpret this information, identify the required services, and estimate the quantities. And this information is not always complete or consistently structured. So the engineer may also need to compare the inquiry with previous offers and project information. So the problem is not simply that quotation preparation takes time. The process also depends on the individual interpretation, which can affect consistency and traceability. So this led us to our main practical question. Can an LLM produce a sufficiently accurate first proposal for engineer review? So the aim here was not to demonstrate like full automation, but to determine whether the model output is useful enough to support the existing workflow. So we structured the evaluation around three research questions. First was service selection. So can the model identify the correct items from the company's service list based on the inquiry? Second was quantity generation. So can it determine the required numerical quantities reliably? And third was operational feasibility. So how do the models compare in terms of both output quality and processing time? We compared commercial and open source models, and for some models we also tested whether adding attachments improved the results. And the use case is based on the data from company operating in geotechnical investigations. So the existing quotation preparation workflow starts when the client inquiry is received. The engineer reviews the inquiry, identifies the appropriate geotechnical investigation, selects the relevant service items, and then estimates their quantities. Then the engineer prepares the proposed scope and the full quotation, and the manager reviews the documents before it's sent to the client. So several of these steps are repetitive, but they are not completely deterministic. So this means that two engineers may interpret the same inquiry differently, particularly when information is incomplete or when the required scope is only indirectly described. So in our proposed workflow, the LLM supports the interpretation and drafting stages. So the inquiry is provided to the LLM together with relevant domain context. The model then proposes service items, quantities, and a structured response. The engineer reviews this proposal, corrects it where it's necessary, and approves the result. And after that, the quotation process can continue through the normal preparation and the management review process. So the main point is that the model does not replace the engineer. The LLM proposes, engineer then checks, corrects, and approves. And this human-in-the-loop structure is particularly important because quotation decisions have both technical and financial consequences. So here in this case, the responsibility stays with the engineer. So for our evaluation, we used real inquiry quotation pairs collected over several years from a geotechnical engineering company, and each pair contained an anonymized client inquiry and the corresponding engineer-approved quotation. The data was then divided into training and test pairs. So training data was only used for fine-tuning the open source models, and the same 120 pair test set was used to evaluate all model configurations. The models then received the inquiry text, attachments were applicable, and domain knowledge. Okay, so the required output was a structured JSON. So for every proposed item, the model had to provide the service name and its quantity. And service selection was evaluating using precision, recall, and F1 score. And we also measured quantity, accuracy, and processing time. So we evaluated 5 main models. The commercial models were GPT 4.1 and GPT-5 and Claude Sonnet 4.5. The GPT 4.1 and 5 were also tested with attachments plus the inquiry text. And for the open source alternative, we used Qwen with 32 billion parameters in its base form and as a fine-tuned version. And the training the model was carried out in 2 stages. First, we did domain adaptation with text describing the company's geotechnical services. Then it was fine-tuned on inquiry-quotation pairs to improve service selection. And we didn't use retrieval, augmented generation, or any other external tool integration in this experiment. So this graph compares the service selection F1 scores with the average processing time per inquiry. GPT-5 with attachments achieved the highest F1 score at approximately 50%, but processing time took approximately 133 seconds per inquiry. Sonnet achieved the F1 score at 48%, while requiring about 7 seconds of processing time. So in our experiment, it was the strongest balance between quality and time. And as it's seen in the graph, the commercial models clearly outperformed the 2 open source configurations. Fine-tuning Qwen improved its F1 score from 8 to 18%, but it remained below the commercial models, and processing time was still relatively slow. And an additional finding is that attachments did not improve performance consistently. They improved the performance for GPT-5, but reduced with GPT 4.1. So here, simply adding more context was not automatically beneficial. Okay, and the quantity results were considerably weaker in this case. So the best performing configuration, GPT-5 with attachments, achieved a quantity accuracy of 15%, and without attachment it reached 13%, and Sonnet reached 11%, and the remaining configurations were even below that level. So this shows an important difference between semantic matching and numerical determination. So for practical implementations, quantity should not be accepted directly from unconstrained LLM. They need to be calculated or checked using deterministic rules and expert review. So taken together, the results do not support the autonomous quotation preparation with LLM. For service selection, the models can produce a useful first proposal, but even the best configuration reached around 50% F1 score. Quantity determination is a clear limitation, so with a maximum accuracy of 15%, quantities should not be accepted directly from the LLM. The important note here is also that this research was carried out last year, so the results today might be different. So yeah, the realistic solution is a hybrid workflow. The LLM supports interpretation and drafting. Deterministic tools handle the calculations, and the engineer remains responsible for validation and approval. Okay, thank you.